class we're going to look at how to write empirical formulas for compounds. So we talked a little bit about empirical formulas when we talked about the difference between ionic and molecular formulas. Remember, for ionic they were the simplest whole number ratio. Well, that's what an empirical formula is. So a definition of an empirical formula is the simplest whole number ratio of elements in a compound. And that's what an ionic ionic formula is. It's the empirical formula. But a molecule can also have an empirical formula in addition to its molecular formula. So what does that mean? Well, a molecular formula tells me the actual number of atoms of each type in a compound. It is the same or a multiple of the empirical formula. So it might be the same, it might be different. Here's an example. Benzene. Benzene is an industrial cleaner. And here's its composition. If you look at benzene, it's a ring, and it's got 6 carbons, 1, 2, 3, 4, 5, 6, and 6 hydrogens, 1, 2, 3, 4, 5, 6. So its molecular formula, what tells me what the molecule is C6H6. That's what benzene is, and that's what chemists recognize as benzene. But its empirical formula is CH. There's 1 atom of carbon for every 1 atom of hydrogen, or 1 mole of atoms of carbon to 1 mole of atoms of hydrogen. Okay, so here's a long list of an approach you can use to try to figure out what the empirical formula is. So here's a problem. So let's say someone had a sample and they sent it to a lab. They wanted to know what was in it. And the scientists run this through some expensive analytical equipment, and it comes back and tells it the sample contains 36.5 grams of sodium, 38.1% oxygen, and 25.4% sulfur. Well, in order to figure out the empirical formula, what I have to do is get this to moles, and what I'm dealing with is percentages here. So the trick to this is to assume that you have a 100-gram sample. And if you have a 100-gram sample, then you know you've got 36.5 grams of sodium, 38.1 grams of oxygen, and 25.4 grams of sulfur. From this, I can figure out how many moles I have and the ratio of moles for each atom, and that will lead me to my empirical formula. So let's see how it works. So the first thing is we assume we have a 100-gram sample. And if my sample is 100 grams and 36.5% is sodium, then I have 36.5 grams of sodium, and so on. Okay. Then I take and I can calculate, if I know the mass of each element, I can calculate the moles for each element. And what I do is I use factor label, and so 36.5 grams of sodium times 1 mole of sodium is 23 grams of sodium, gives me 1.59 moles of sodium. I do the same thing for oxygen, and I end up with 2.38 moles of oxygen. Do the same thing for sulfur, and I end up with 0.79 moles of sulfur. Okay, so the third step is to divide all the answers, all the number of moles I get in step 2 by the smallest number. And the smallest number of moles was sodium's at 0.79, so I divide the number of moles, the smallest number of moles was sulfur's at 0.79. I divide them all by 0.79, and I get 2 for sodium, 3 for oxygen, and 1 for sulfur. Okay, and so this is how I come out with the simplest simplest whole number ratio, smallest whole number ratio of this rate. It's just a sort of a math trick for figuring out the least common multiple. Okay, so if the work in step 3 gives me whole numbers, then I'm done, and I use these numbers to write the empirical formula. And in this case, I am done. I've got whole numbers, 2, 3, and 1, or pretty close to it. So I use those as my subscript, Na2O3S. And knowing a little bit about chemistry, I know that that's going to be sodium with a sulfite ion. And it makes sense because this is a -2, sodium's a +1, so that's a balanced formula. Okay, so that's how it worked for the first one. Let's do another one. Alright, for this one, I need to determine the empirical formula for a compound composed of 85.47% manganese and 14.53% nitrogen. So again, I'm going to assume I have a 100 gram sample, which gives me 85.47 grams of manganese and 14.53 grams of nitrogen. I got to figure out the number of moles for each element, and for manganese I end up with 1.56 moles, and for nitrogen I end up with 1.04 moles. So I'm going to divide both of these by the smaller of the two numbers, which would be 1.04 moles of nitrogen, and when I do that I get 1.5 for manganese, and nitrogen is 1.0. So remember, it said if you get the whole number ratios, whole numbers in this step, that I'm done. But I don't have whole numbers. I've got 1.5 and 1, and I can't write a formula that says Mn 1.5 and N1. I need to have whole numbers in my subscript. So if it's not a whole number, what you need to do is multiply this times some whole number to get the simplest whole number ratio. And I can just multiply this times 2 will give me 3, and I can multiply this times 2 and give me 1. I got to multiply both factors times the same whole number. So if I multiply them by 2, I get 3.0 and 2.0, and that will give me my formula, Mn3N2. I want the simplest whole number, and that's how I'm going to do that. Alright, that's going to do it.